rate from minimum, low, medium to minimum. Continuous flow meter, small spinner, good for small tubing size also, good for high flow rate, this one. But full bore, it have limitation because the spinner manufacturer or the tool manufacturer, they give you like table with limitation. That's why when you want to design to plan any job, you need to know the maximum rate in the well to put the right spinner. Because sometimes, let's say, if you put, like example, full bore and you have like high rate, then this one it became like saturated. They rotate to the maximum, and then they cannot detect it any flow rate more than the maximum, which is designed for. So if you make your interpretation, you get like your rate, it's completely less. So for this case, it's better to run either this one or this one, the continuous or continuous energy, what we call CFG, this one. And also sometimes, if you run this one or this one in low flow rate, you cannot see anything. So you need to run the basket flow rate. So the selection of the spinner type, it's very important. You need at least to know the maximum flow rate. And then, because any manufacturer of production rig tool, they give us like table with limitation. So you know the spinner, it's have this limitation. So for that, you can choose the right one from the beginning. You cannot run, let's say, for example, low flow rate and you run this one. So you cannot see anything. So that's what you call pedal basket. This one, stationary measurement, the last one. So this one, of course, is good for low. Yes.
Sorry, I have a question here. Sorry, I interrupted you. Just in case, if we want, for example, to run both, like one full bore spinner and another inline spinner in the same tool string, and I mean, they will give definitely a little bit different, how to say, estimation of the flow rate. And I wonder which one to take into consideration. I mean, which is the one,
Yeah. Let's say if you are in single phase, most of the case it will be the same. But usually, the inline, if you like put your make like centralization. It's well centralized in the well bore. Let's say you put 3 centralizer. If it's single phase, let's say water or whatever, gas or oil, I expect it to get the same spinner behavior, the same response. Okay, when you make the calibration, and then you get same fluid velocity. But if you have like multi-phase, so it depends on your flow regime. Because flow regime, there is mist annular flow, there is slag flow, there is froth. So it depends, because the inline spinner, this one, it should be in the center, and also the blade, it's small, it's inside. But this one, it's more exposed.
The coverage is more, you know?
Yeah. And when the coverage is more, now we will see why we have the apparent and average. You get my point? So this one, it will measure the maximum flow, because when you have flow like this, you have a parabolic profile. We don't expect it if you have pipe and you have flow, it's like straight. It's never happened. So you have like something. That's why we are going to see what the Reynolds number and viscosity, the effect of the flow regime.
Fair enough.
Yeah.
Thank you.
So now also we have the density. For density, we have 3 different type. We have the which is for me is the best one. But the problem, because we have like source. So many operator company, they try to avoid to run in the well the radioactive one for the density. And also for the calibration for fluid density radioactive, usually we need at least what we call 3 points, or maybe even 4, because the calibration, here I don't bring the calibration chart, because it's linear. Mainly, if let's say if you have water, it's linear from 0 to 1. Let's say from air to fresh water, it's linear. When you get salt water, it's another slope. So the advice, when we run radioactive fluid density, always we need to ask our engineer, field engineer, to make 3-point calibration, not 2. I mean, he take air and he take, let's say, diesel, fresh water, and salt water. 4, it's better. So this is for the radioactive. And also we have fluid density differential pressure. This one, it's like what we measure the difference, because we have like delta P. It's like, it's similar when you have like your pressure curve, and you make the derivative of pressure, it's density, isn't it? Sorry. So this one is differential, but differential, always we have this what we call friction effect. Because when you have the flow, you have the friction. So we need to make correction for the friction effect. Otherwise, for the FDR, no need. And also we have another type, which is fork density, or what we call with the vibration. Here you have like fork, and it's vibrate. And of course, it depends on the type of fluid between those. You have this sound, the vibration, how it's the frequency. So we are using this one also, it's good, but also from my experience, because I use the Spartak one and Sondex one, it have limitation mainly in the high viscous oil. Sometimes high viscous oil of around 0.9693 gram per cc, it's rated sometime 1, like fresh water. Sorry. So we have this three type of density, fluid density classification. After that, we have also the capacitance. Capacitance, we have like 2 plates, and then we have like capacitor, and then of course we have the electric properties is different between hydrocarbon, let's say between oil, gas, and water. It doesn't say. We have the dielectric properties of the fluid. So it's like different. I know this value is for water, this value is for gas, and this value is for oil. From this tool, I can know what type of fluid I have inside. Of course, now if I have mixture, because I can make the calibration and then it's give me the percentage. So that's why the density and the capacitance, this tool give me the hold up. The hold up when I have like multi phase flow, I mean have mixture, let's say from light phase, let's say oil, and I have heavy phase water, and are mixed together. So from density, I can calculate the hold up, and also from density, I can know, for example, I have 30% water and I have 70% oil. Now the pressure. The pressure, same as the pressure gauge. It's by the vibration. When we are, I mean, cement in the quartz itself, it gives us like vibration, and also it's transformed to electricity. So really one, and of course pressure also it have like calibration. So they know, for example, 1000 psi, they give us this value of voltage. 2000, they give me this value. So that's why this one. Only make like, we know that, for example, if I make like pressure test in the lubricator, and I know this value, and I can check the tool is reading the same value or not. Temperature is platinum resistor sensor, the same things here, and this gives us when we have like more heat, the electricity here also change, and they can get the temperature. The same things here, because we have the master calibration, and I can know my downhole temperature. So I think in this stage now, this the last question about the horizontal well. So this tool, it's designed for horizontal well, multi-array tools. Why we use this one? Because the flow regime here, the standard production logging is designed for vertical well, where we have turbulent flow regime. Everything is mixed together. But if you have like stratified flow regime, I mean, each phase, its flow itself. Let's say in horizontal pipe, if you have water oil and gas. Of course, we see water in the bottom, oil in the middle, and the gas in the bottom and the top. So if we take the tool, normal production logging tool, inside, I have one spinner. Part of it will rotate inside water, the other part inside the oil, and the other part inside gas. However, the three phases are flowing different velocities. It's not the same velocity. Let's say if I have like 91 degree, it means 91 degree. I have the slope on the hillside is not on the toe side of the well. So of course the water, it will run faster because we are in the slope. Gas, it's tend to go up, and oil. So I have two different fluid velocities, and then sometime a spinner, I have one video, I can show it to you later on. Spinner, sometimes you have like two phases. One is going up, down, and the spinner, it doesn't give any rotation. This time I'm talking about the standard one. So people, they come with the idea to make like different spinner, different, to be in the different position, to catch gas phase, oil phase, and water phase. So you see here, because let's say here I have gas, because it's in the top. I have the slope, it's from toe to heel side, and I have here water. Water is go down due to the gravity. So what I have, if I have my spinner here, if those two velocity are equal but in two different direction, what's happened to my spinner? It doesn't rotate, the normal one. But if I bring what we call this tool, the multi-array tool, I have like here, I have 6 spinners. So I know I have this one in the water, so it will give me negative. This one, oil and gas, it will give me positive. So I know the flow regime here. Okay, and also for the other sensor, for hold up, for density, for everything, it's like that's what they call multi-array tool. So this one, it's designed for the highly deviated well and for horizontal well. So I never seen that for multi-phase normal standard production logging tool. It never we ran before many time, even when I'm in Hassim Saud. But once they bring, when you see mainly with this multi-array tool, Schlumberger one, it's FSI, it's really amazing. Even you can see like, they can give you like video to see the flow regime, what's going on. When the water is going up, down, you can see everything.
Farid, we have a few questions here before we move on. I believe the first one is from Walid, and he's asking, do metal loss of casing affect resistivity?
Metal loss? He mean about CCL or?
I think so, because we
CCL it's sensitive, but it's not very, very sensitive. I mean, if you have like big loss, let's say if you have like your tubing, it's completely ruptured. I mean, you can see. Sometime across the perforation, you see that's what we call noisy CCL. Even we can see it in some example, because in the perforation you create a hole, so you have less metal. Okay, so you see that's the response of the spinner across the body, which is not perforated, and across the area which is perforated is different. You can see what we call it is noisy CCL. You can see CCL is react differently, so it's give you an indication there is something, but it's not as like a corrosion tool to give me like with more details, but to give you an indication this is the perforation. And that's sometime I detected that there is off depth perforation from CCL and from caliper, because they give you the perforation, and when you make it in the software, and after that you see that sometimes even a spinner show that the influence coming from place which is not should be not perforated. But if you go to CCL caliper, then you see, oh, this is the perforation. And sometimes if you have like some deposits, salt or scales radioactive, even you can see in this area.
Fair enough. Then the other question is from Amira, and she's asking, we need a gamma ray for this type of density. I believe she is talking about the density from the radioactive
nuclear.
The nuclear,
radioactive,
Yeah.
No. It's the tool itself. It's measuring the gamma ray. We don't need gamma ray sensor. We have the gamma ray, but the what we call the tool itself. Just 1 second. Yeah, here. Yeah, we have gamma ray detector.
But
Yes.
it's not natural gamma ray.
It's not. No. It's detecting what's happening here because even this one is same as the density open hole, but it's small scale. Even with this one, sometime if it's not well centralized, or if we have also, I forget to talk about the inconvenience for this one because it's like window. Sometimes if you have like trapped debris or something inside, it's give you wrong.
Okay.
Let's say if you have some water with like mud, something it's keeping in the sump on the bottom of the well. If it's catch here, sometimes what we do, we run with fast speed, cable speed to clean it. Yeah.
So the other question is from Saliha. She's saying the velocity determined by the spinner
Yeah.
seems to be an average. How can we determine the velocity of each phase or each fluid, individual fluid, as she said?
Okay. So she talked about the standard production logging in vertical well. Yeah. Mainly, first of all, we make what we call apparent fluid velocity. Then we get the average one. After that, we make rate, total rate. Now I have the total rate. Now I want to split the rate on two phase, let's say, because now we have in the next slide, but I can give brief. Since I have, if I know that from my density tool and from my capacitance, I have, let's say, 30% water, 70% oil. So then I can calculate the water rate and the oil rate. But the problem is not easy like that, because when you have two phases flowing together, we have what we call slippage velocity, which affects slippage velocity. Unfortunately, there is no equation. It's about correlation. I need to choose like Douglas and Brown, different correlation. Okay, they make it sometime in the lab, some correlation, they make it like with some algorithm. So the slippage velocity, and then I can get from slippage velocity, I can get water velocity how much and oil velocity how much, but it's from correlation.
Okay.
If she talk about the horizontal well, the good things about horizontal well, we have like stratified flow. The slippage velocity time is zero because each flow is flowing itself. And also I have directly the sensor like spinner. It's measuring directly the flow. So for the multi-array tool, I can get directly. I know oil phase, how much velocity, get it directly.
Okay, good. Actually, is and spinners be used to identify which perforation in a well are producing rates?
Yeah, so the spinner, it's the respective spinner or rotation and on the velocity. I mean, high velocity, high flow rate, high rotation. Even from the raw data, I can see spinner is like increasing. You see like stopping spinner. So you know that this zone is contributing. And you can see it in the example. You can see directly.
Fair enough.
Yeah.
Okay, the last question from Muhammad. He says caliper for friction correction. I don't know if that's a question or
No, caliper, I know. Sometimes we use caliper for roughness because, you know, with flow regime, there is also, you can find it in the interpretation software. We can take the caliper data to calculate the roughness. Because roughness, what mean? We don't imagine that the pipe inside is like smooth. Of course, there is first from the factory, the pipe is never like smooth. So this one, it's affect the flow. What we call roughness, it's small correction. You can use the caliper, or you can use also you can get the what we call roughness is to correct. I mean, it's not smooth. The pipe is not, I mean, 100% smooth. There is like small change between in the diameter, which make affect in the flow regime itself. So this one we think is not really have big effect in the data. Even if you don't do it, it doesn't, I mean, make big difference.
Okay, good. So I believe those are the questions. We have another one.
Okay.
So it's from Abdelha.
Resistance array tool is mainly for, it's give you, I mean, hydrocarbon is resistant active. So this is the idea. It's small, and then you have like small probe and another probe. So when any drop of water flow through it, so it smells like they see the conductivity or the resistivity, and it's counting. That's it. Yeah.
I have a question here,
Yes.
if you don't mind. You specify this resistance array tool, and then
Array tool.
yes, the capacitance
It's
rating.
capacitance.
Yeah.
One is capacitance. This one is measuring capacity.
Yes. What
This
what,
one is
what yeah.
yes.
What are the limitation of these tools? I mean, if for
Yes,
example,
yes, yes.
yes,
Of course, there is limitation about the accuracy. Of course, when you have like, let's say in this case, sometime if you have like, let's say water cut or water hold up, it's more than 70. You have like, is not very accurate. The high water cut or high water hold up, you don't expect that accurate measurement. If it's less than 70, it's okay. Mainly for capacitance. Here, let's say, because this one we need maybe, because different tools they have like limitation, and like this one, so it depends also the, when they design the tool, they design it that they can catch the bubble or the drop of water. Sometime maybe the tool they cannot all the what's going on, and also they take that's in it's like turbulent. Sometimes it's here. I mean continuous. But sometimes it's not the case. For example, sometimes when you have like mist and air flow, or you have froth flow or slag flow, it depends. But it's give you this tool. I used it before. Really, it's give you the flow regime down. You can see what's going on.
okay, but for this tool, this is interesting because you said this resistance array tool cannot differentiate between hydrocarbons. I mean, gas or oil, they are both resistive.
What they use?
How can,
Yeah,
yeah,
usually they use both. Now there is another one. Maybe there is what you call optical. This one is SAT. This one is 4D. There is optical. Now even I think Baker use on next they have. There is optical tool. What we call gas hold up. It's mainly for gas. Same because Schlumberger they have like depth tool, the electric, this one, and they have optical here instead of have this probe, electrical probe. No, they have they sell Viber, and they have light. So of course the light when it's cross gas, it's different when it's cross liquid, either either oil or water. You get my point? Because water, oil, opacity, not clear. Gas is
so
clear.
gas content.
Gas. And from this we no, from this we can get gas, and from this we can get water. So when you get, so now you can get oil from this and this. You get, and usually we cannot, like here we cannot run rats. If you have like three, if your phase is not a problem. If you have three phase, we need to run like this, cut and cut. Okay, it cut. Both.
Okay, thank you.
Yeah. So Okay, so this one is the spinner, small one. You see, it's like turbine side. So they have this miniature flow and of course it will be this position for horizontal well because we have stratified flow. You can see the map view. That's what I talk about the flow regime. Even I know for FSI, they give you like movie where you see the well when you log from A to Z, how the water bubble entering inside the well, how gas, everything. You can get it at movie, and you can see here. You see, for example, here the flow regime how it's going. So all this, I mean, the map view, this view is coming from all the sensor because you have more data. You have like 12 sensor and you have like 6 sensor for spinner. So you can catch every layer what's going on. And matter of fluid. Of course, because this one is like cost-wise. Of course, when you run military tool, is not the same cost as the standard tool. It's cost effective. So most of the operator company they are not using like frequently, but when they need it, they use it. And also the problem for horizontal well, if it's open hole, it's sometimes challenging. Mainly if like not like hard reservoir, it's like sandstone when you have like different. But anyhow, even if access to one data, you can make your interpretation and you can get your results.
For me to clarify. So in this case, if we have a horizontal well with multi-phase flow, like water, gas, and oil, and we are running this cat and rat together, we can know the capacitance and the resistance of each phase. Do we need the PVT or no in this case, like the conventional PLT or no?
This one, you need PVT just to convert from downhole to surface.
You need BO or BG and that's it.
Yeah, you need convert. Usually because you have, you have your, maybe you need also to estimate the viscosity down, but it's not affect, I mean, same case for the vertical one. Because when you use PVT, you have PVT affects your Reynolds number, so you need PVT. Okay, and also to convert from surface to downhole and the inverse. But for this case, if you have like your hold up, you have like your phase velocity, is not
Okay.
really affecting load. Yeah. So the question of the cost, there is a limitation in high speed. Yeah, you are right. I remember even it's not only in the high speed or either Ghost, they make like calibration. They have like threshold. It's happened to me one time when I'm in Hassim Saud. I make interpretation with the density because we have well tests and I get the results okay. But when I use depth, I get at this time more water. To put threshold at what level because it depends also on the salinity because also it has some time oil we know that's always salinity it's related to the water but sometimes you have like some oil it's like I mean with small fine drop of water is still there then I mean the tool it's counting oil as water. So in this case, we need to change the threshold. We tell the tool, no. Start counting if I have this salinity. When I say salinity, I mean resistivity. It's different. So for this, to be careful. I mean, different area, you can take sample from your reservoir and give it to the server to make the right threshold for depth tool. It's happened to me. Yes, right. And also, of course, with high flow, of high speed, sometimes even the ghost it can. And also sometimes ghost if they don't use a new one, sometimes it's like scratched. When it's scratched, it doesn't give you the same light intensity. They know that they can. This one it's entering in the quality control system and job planning. You need to check all these things before. So okay, let's move now. I think. Okay, I don't know. We already. So no need to stay here. So the second section, which means this is the main one, spinner. So we're going to talk about spinner. I think we still have time. Spinner response and calibration, cross plot, apparent and average fluid velocity, and the end rate calculation single phase, and some examples just to show how it looks the spinner data, production logging data, and how we can make production injection profile. So here what's going to do, let's forget completely the two. Back when we are kids, we are playing with what we call I don't know, this paper fan. I think everyone do it, either with bottle of plastic bottle, Javel ولا ما عارف. And also we try to understand how the spinner respond to the fluid movement and to the cable movement. Because what we have and we are running inside. So this one is our windy day, the wind, and this is our tool spinner, and the cable is the boy. He's running forward and back. So let's start with the first scenario, first case. So what I have no wind. I mean no windy day, no wind, and I have the boy. It's running forward. So forward, when I give this plus, it means forward, plus 10 meter per minute. And let's observe this paper fan. Okay, in a direction. Let's say it's rotating this direction. Let's say from right to left. And when I count the rotation, I get 3 rotation per second. Okay, this is the first case. No wind. It means I have 0 meter per minute. No wind. Boy ran forward at 10 at plus 10 meter per minute. So the paper fan rotates at plus 3 revolution per second. So let's move to the second case. The boy, he wants to stop and stand up. It means velocity is 0 meter per minute. But at this time, there is wind which is blowing, airflow. Sorry. This airflow, it was 10 meter per minute. Sorry. What we observe that the paper fan rotates in the same direction plus 3. So in this case, what we see? So that you see, boy stand up, 0 meter per minute, wind flow at 10 meter per minute, paper fan rotate plus 3. Okay. So what I can understand from these two cases, that's the effect on the our spinner, this paper fan. If I have any flow against it, 10 meter per minute is rotate 3. And if I run inside any mass, because here we have air, it's mass. Only in this case, the air is not flowing, is not moving, but the air is there. I have mass of air. So what's happened? The boy is running inside the mass of air, which make the paper fan rotate 3 RPS on the positive side. So now let's move to the third. Sorry.
Go slow, Farid. We need you. We are running like 4 sessions. Don't rush. We have all the time.
عندي العائله، قلت لك العائله اليوم كانت في الامرجنسي طايشه في الدار 40 درجه. ربي يستر. Anyhow, let's combine.
take some honey, Mr. Farid.
والله عندي العسل تاع اليمن تاع عمان، بس ربي يستر. وش اقول لك، فيروس كورونا هذا مخلفات ربي.
طهور ان شاء الله، طهور ان شاء الله.
ان شاء الله، الله يبارك فيك. So let's combine these two cases. So what I mean, I have the boys running forward plus 10 meter per minute, and also I have airflow or wind that's blowing at 10 meter per minute. Because we have seen in this case, it's acting in the same direction. I mean, even if I don't have any wind, I mean, everything is stable, but I am the buoy. It's running inside the mass of air. It's +3. It's in the positive side. When the wind or airflow it's blow, so it's 3 RPS. So logically, I have here resultant of 2 force acting in the same direction. So what I mean here, I have 6 revolution per second. So here, when I have buoy run forward at 10 meters per minute and the wind flow at 10 meters per minute, paper fan rotate. Now I have resultant. I mean, +3, I have +6. I think here it's clear, yeah?
It's kind of, how to say, relative velocity. If you have two velocities together,
yes,
so
exactly.
they will combine. If they are in opposite direction, they will subtract.
Yes, so that's why. Conclusion, buoy run against wind flow. When the buoy it's running against the wind flow here, this is on increasing on paper fan rotation. Effect of buoy and wind in the same rotation direction of the paper fan. It's give me, I mean, like it's resultant of 2 force in the same. It's adding. Okay. Now let's move to the fourth scenario. Now the buoy it's running backward. Okay. And here it's no wind. So the paper fan it's rotating the other side, which we give us minus sign, negative side, which we call it negative side, -3 because it's running -10. So now let's see. The buoy stand by and stop going backward, and we have airflow or wind it's blow at 10 meters per minute. Always is 3 RPS. Same. Okay. So now let's combine these 2 figures. What's happened? The buoy it's running here, and we have airflow or wind blow at 10 meters per minute. This one, because it's make it in the other side, -3. This one, it's +3. So -3 +3, this one is 0. Okay. So even here, if, for example, we don't know the airflow how much, if the buoy he ran with the speed and he see, I mean, he's measuring his speed, he can deduct and understand that's if the paper fan stop rotate, it means he's running with the same speed of airflow. So here, buoy run with wind flow results on no rotation, effect of buoy and wind in the opposite rotation direction of the paper fan. That's why here it doesn't rotate, because this one it's acting to get +3, and the buoy, because it's moving forward, it's -3. So +3 -3, it's 0. So let's move now. We have another figure. So now let's say the buoy increases speed from 10 to 20, +20, forward. And the wind blew at the same speed, 10 meters per minute. So what's happened? Because he's double his speed. Before we see at 10, 3. Now at 20, it's 6. And from the wind effect, it's 3. So it means 9. So when the buoy ran forward, wind flow plus 20 meters per minute, wind flow at 10 meters per minute, paper fan rotate 10 meters RPS. Let's see the other figure now. It's backward, but double his speed, -20. And here, the wind, it's at 10 meters per minute. Here, because it's -20, expect to get -6. And here it's +3. So -6 +3, it's -3. So what we can conclude from that's if the buoy ran against wind flow, buoy speed more than wind speed. What's happened? Results on increasing on paper fan rotation. So we are talking about this one. Let's say we have the wind velocity, it's like constant, 10. But now the buoy, it's increasing his speed, 10, 20, 30, 30, and 40. What we expected? We expected to get like increasing because he's acting always in the same direction because he's running against the airflow. So always you have more RPS. But in the other case, boy, when he ran with wind flow, boy speed less than wind speed results on decreasing on paper fan rotation, effect of boy and wind in the opposite rotation. I mean when he is going backward. So that's why here, when he's going backward, if the speed of the boy it's more than the speed of the wind, we never get positive RPS. Because they are acting in two different directions. I mean, it's like resultant of two force. It means when the boy is moving forward, he tries to rotate the paper fan in the negative side, but the wind in the positive side. So when we can get like positive value, when the wind flow, it's more. Let's say in this, I don't put it here. Let's say, for example, here I have 30 meters per minute. 30 meters per minute, now I get 3 RPS. Plus 3. It's rotating the other side. So this one is like illustration how it's now we can convert all this. So say this is the cable speed, this is the flow speed, and this is our tool. It's the same. Now we can move.
Farid, sorry.
Yes.
We have maybe like 5 to 10 minutes more, so maybe we will open the window to any questions. Anybody have any questions can ask directly, like open the mic, ask. None, we will maybe resume in another maybe session because it's already more than 1 hour.
Oh.
So any questions?
Hi, actually, I do have a question.
Yeah, welcome.
Okay, so how do we decide which correlation to use in our model? For example, if it's a 2-phase or a 3-phase, there are so many correlations.
Yeah. This is the question everyone he asked about it. Even I remember asking, I don't know if they did win. Because those correlation, it's made. I mean, some of them even it's made like in surface. Which what you can say, because there are some operator company, they make their own correlation. They take their their fluid from the reservoir, make their own lab correlation or what you can name it. Okay, so now every correlation you can find like it give you like small summary. This one it's more adequate for, let's say, for highly deviated well. This one it's more adequate for condensate gas. This one it's more adequate for oil well, and then you can choose. And also per your experience, and when you work different in the same area, when you make different processing, you can choose. And of course, there is common one, which is like Duckler and then Brown. This is the two. I don't know. Here, maybe next time you can even open Emerald and we can show the correlation, what's going, and we can go one by one. So yeah. So for the shoes of the correlation, it needs some. Some experience. Some when you make like different interpretation, you can pick one which is like fit with in your area. Depend, because the correlation depends on the fluid viscosity, depend on the deviation itself. So that's why. But for me, the common one is like Duckler and then the Brown. Sometime let's like be like, because usually when we do PLT, also we have well test on surface, yeah. So when you make your interpretation, you get your rate, you convert it to standard rate, surface rate. First of all, if you are confident about your PVT, if you are like 100% confident that the PPT which you use, it's like accurate. And after that, you get that you have less, let's say, less oil or less water. This one is coming from relation, slippage velocity, because slippage velocity, it's reducing the heavy phase velocity. Let's say if you have oil and gas, if you take Daklar and if you take Petal and Aziz, it's completely different. I know that Petal and Aziz give you less less heavy phase. So in this case, brown between. That's the answer your question.
Is that it? I believe. Any other questions? We will wait for maybe 10 seconds. Anybody?
Assalamu alaikum. So, yeah, so I was actually interested in the which I think will not be covered this night, the SIP. So will there ask a question?
Okay. Feel free.
If you have any examples in SIP in gas wells.
Yes, but you know, SIP, they need to do it with the correct way. Because here we do mitigate, but sometimes it's not with the right way. Because you need how long you shut the well, and how, even me to I'm not like specialist, because I think this one is more related. Maybe he can help us. We can, okay, let's see. We need to SIP, just 1 second. I want to show you. Yeah, let's go quickly here. Yeah, no problem. Okay, let's. Sorry, I need to go quickly. Sorry, just 1 second. You got lost with this. Okay, let's quickly move next. Let's do it with another way. Sorry. Okay. Now you get my screen, yeah?
Yes.
Okay. So here, what I mean about the correct way. So you know, to know the period of shutting and then flowing, depend on your that's what you call isochronal test. To be honest, even me, I'm not specialized in that. So modify the isochronal test. So that's why. So what we are aiming from SIP is to get the relationship between, inflow between rate and pressure, downward pressure. So we have example here. It's real. This one is real example. It's not. But they do it more. Also, you want reservoir pressure from this one. You see, so you can get absolute outflow. This one is gas well, and this 1, 3, and 4 rates. This one is real data. They open for the first, and then they close. This one's the pressure, and this one is the pressure. Mix the velocity from both. See, from IS and from TFG. And this is the pressure, and this is the pressures. For different, and also shutting. You have cross flow during shutting. Here, the different contribution, the pressure from that, and this is what they use. The IPR. So then do one. So we can, of course, here we call C and N or. So here we have the absolute outflow, and also you can get the pressure, reservoir pressure estimated from SSB. But you need to do it in the correct way. But sometimes they don't. I mean, mainly between the flow type. Open the well and then close for a period, and then you do your that's what is this straight line like liquid or LIT or
Usually it's CNN because you have the
CNN. That's because
Yeah.
here me I work, but the problem
Yeah.
sometimes just I give them just like quality, like indication, but I know that they're not doing it that way because we need at the beginning to make a test. I mean, as a book, it's not only time they close for 5 hours, time do it stabilization for 6. It's not really, I mean, mainly for gas. So they are not doing, I mean, with the proper way. So that's it. This is my answer about SIP. It's good if you do it the proper way. You can get the good things in Amrod. They have, and also it's give you, if you have cross flow, you can see even when you do your SIP. I can see it. It's like another matter of QC. It's mainly if you have like cross flow, sometimes even has chlorine flowing, and in many type of
Yeah,
well. So yeah, it's there, but unfortunately many people they are not using it with
Yeah,
with
because in layered reservoir, usually, when you test layer,
yeah,
you have IPR, but you have the when you open the well, the behavior will be different.
yeah,
So this SIP is the best way to have your
it's good.
commented.
Yeah,
Yes, you have contribution
yes,
each one, and you have the the
yeah.
overall. Yeah.
Yeah, it's good. It's good. When you usually when you make multi rate, it's better to get. But the problem here, what I have seen, because for me, when I make interpretation, I have different rates. I have shutting. I try to do it myself. In this case, it's like it was like, and they make it with the good way. I know the senior PT, it's a good guy. He make it with the proper way. So you get this. Sometimes you cannot get this line. You cannot get like, I mean, matching with LIT or straight line, of course, unless you have like single phase, you can use it. Like well, it's easy, but like for gas, you need to do it with the proper way. But it's good, like for kappa, it's there. You can use it. Some things what they call apparent permeability, which is good also. But you need to get like correct permeability and to get like perfectly do your job. To be honest, I never tried it. I want to try it one time to get permeability from MPLT, which is good. You can correlate if you have any permeability data.
Okay. Thank you.
Okay, you're welcome.
Any other questions? One. So I think that's it. Once again, I'd like to remind about our how to say our calendar, and just let me share my screen. Do you see my screen?
Yeah.
So to Mr. Farid Mekhzoumi, thanks to him, we've
We can see your
you can
in the
maybe he
Yeah.
stop, and then I will share.
Yeah. So I stop my. Okay, stop. No problem.
What about now, Walid? Do you see my screen?
Yeah.
Yes, we do.
Okay. So today, in today's session, we've talked about the introduction to production logging, and then Farid with the single phase.
Yeah.
So I think it will take more time. In the next webinars, maybe it will take us 2 weeks. We don't know. It depends on the availability of Mr. Farid, first of all, and then the time of the questions and everything. We will try to be as he can elaborate as much as he can.
So the next session, it will be mainly for spinner calibration, and then to get like single phase. Maybe start to phase some subjects. And that's it.
Good. So thank you again for all attendees here. Thank you, Mr. Farid, for this very informative presentation. And we look forward to have you again in our chapter.
Inshallah.
Thank you, everyone. Thank you.
Thank you.
Thank you very much. Thank you.